year with having 2 of our musicals this year being Disney and then Frozen coming out.
And Disney's just also my life, so that's why we
chose this topic, and so we're kind of taking it as if Disney was real life, this would be the real calculations for it.
Yes.
So we're going to first go to Aladdin.
Yes, specifically the Magic Carpet Ride. So, Brianna, why don't you tell me a little about the history of the Magic Carpet?
I would love to tell you the history about the Magic
Wonderful,
Carpet.
Brianna.
The Magic Carpet is in Aladdin, Disney's Aladdin, which was inspired by a Middle Eastern folk tale found in the Book of 1001 Nights, consisting of an impoverished boy tricked into finding a magic lamp by a wicked sorcerer.
There's actually no magic carpet in the original story, so it's a purely Disney invention. And Disney released its movie November 25th, 1992, and it was Disney's 31st full-length animated feature.
So
it's
we
a pretty good one.
have our main character Aladdin, and he rubs the lamp, and then the genie gives him 3 wishes, and on the way he falls in love. And the magic carpet is just the way they get around, and it's one of the magical elements of the movie.
It's also pretty awesome.
That is true.
All right, so we decided to focus a little bit on the velocity of the magic carpet. So, what is velocity, Brianna?
Well, velocity is speed in a given direction.
Very nice, very nice. I believe that was developed by Sir Isaac Newton and Gottfried Leibniz, right? In the fundamental theorem of calculus.
I believe you're correct.
Wonderful.
So the fundamental theory of calculus is focusing on position, velocity, and acceleration functions as derivatives and anti-derivatives of each other. Did you know that?
I did not. That is fascinating. Wow.
How do you use calculus? We didn't know that yet.
Do we have sound on this? It's not going to be
A lot
a straight out
better.
sound.
Yeah, we can.
It's all right. They're just talking. No one needs conversation.
They're saying, let's go find out the velocity of our carpet.
It's pretty fun. Let's really velocity. I don't know. Sure. Let's do it.
Do you trust me? Sure.
Yes. Oh. Look at that. Hand holding. Pretty great stuff. See that? Acceleration. There we go. That's great. There we go. These look like cumulonimbus clouds about 20,000 feet. Pretty high too. So they should probably not be singing this slow.
So what we're going to do with showing this clip is in the movie, it kind of commercializes some of the major landmarks, and we took those landmarks, and that's how we found the distances between each place, and then we add them together to find our average distance overall.
Yes. So we'll be coming up with our first.
I don't think you can actually play with the clouds, so that's an impossible.
Yeah. Hey, look,
Hey,
that's
that's your
Dairy
ice
Queen.
cream.
Yep.
And she's doing the Titanic here, and he totally misses it.
Yep.
Okay, and here's where we start getting to the landmarks.
All right, ready for it? We have Plateau, Egypt.
We have the Sphinx,
Yep.
and we have in Britain.
Nose. And horses. Don't know where that is, but it's somewhere.
Somewhere along their path.
Yeah. Here we are, Parthenon, Athens, Greece. And it doesn't really show.
It doesn't really show the last one. The last one is a replica of the Emperor's Palace in China.
Xiangyang, China.
Xiangyang, China. So
So,
that's about that.
yeah, I hope that was fun for you all. So, by using these landmarks that we found, which started out in Baghdad, Iraq, which is where Aqaba is based, going to East Plateau, Athens, and Xiangyang, we found that the total distance is 8,730.3 miles.
And the total time we used was the time of the song. That's when they started their magic carpet ride, which is 2.583 minutes.
Exactly. So average velocity is the total distance divided by the total time. So just how fast were they going, Brianna?
According to our calculations, they were going 3,379.47 miles a minute. So if we translate that into miles per hour, we have 202,768.25 miles per hour.
Pretty fast.
So their hair should not look pretty.
They really shouldn't have stayed on the carpet.
And they shouldn't have faces. But
Yes. Also, another thing we want to point out, they were not wearing seatbelts. So make sure you're all safe,
Dangerous.
children.
before you go on your carpets.
Exactly. So next, we are moving on to our favorite character, Gaston.
From Disney's movies.
So, just so you all know, I'm sure you're all pretty familiar with the song. He says he eats 5 dozen eggs a day. How many is 5 dozen eggs, Brianna?
Well, we have 5 dozen, and there's 12 eggs in a dozen.
Make sure you carry one.
I got it. We have 60 eggs per day.
Just for breakfast, just so you know.
357 calories per egg.
And that's 21,420 calories for breakfast. Wow, a lot of cholesterol.
And so I did some research on eating raw eggs, and although like a healthy person would eat 1 to 3 raw eggs a day, but since he eats 60, eating that many raw eggs causes a biotin deficiency.
Which contributes to hair loss.
And Gaston says he's covered in hair, so that's
He's a liar. He's
Yep.
probably wearing a wig.
Probably.
Like a Mr. Brandon Weathers.
History of Gaston. So Gaston, like the Magic Carpet, is also a Disney creation.
In the original Beauty and the Beast, which was written in 1740 in France by Madame Gabrielle Suzanne de Lunès, I know, it's pretty great. There's no mention of him. Also, why don't you tell us about when the Disney movie was released?
Okay, so Disney's Beauty and the Beast was released in 1991 and deals mainly, of course, with Gaston, our egg-eating, mirror-kissing, animal-shooting cheater. I would have got that Gaston.
Yep. And just in case you're wondering about the actual contents of the movie, it talks about a girl named Belle who falls in love and likes books and finds inner beauty. Yep.
So the history of ellipsoid formula. So we wanted to take the volume of the eggs that Gaston eats a day. So we focused on an ellipsoid.
Which is a pretty good model for an egg, I would
pretty
say.
good, like that.
It's like a sphere, but it's like stretched.
Like an oval sphere.
Exactly. So, Sir Isaac Newton studied gravity and the attraction of the poles, and he determined that the Earth had to be a type of ellipsoid. So that's when the need for ellipsoid formulas came about.
Colin McLaren and Carl Jacobi expanded Newton's research to spheroids, and Riemann soon followed.
And they developed more than 41 suggested formulas for the volume of the Earth as an ellipsoid, but since those formulas have been generalized, we have a general ellipsoid formula using the 3 different
So
radiuses.
the ellipsoid kind of takes the volume like a sphere. Since we all know the volume of a sphere is 4/3 pi r cubed, an ellipsoid doesn't have the same radii that goes, because if you go out and you come in for each point on a sphere, it's always equal. An ellipsoid, it's not. So we have 3 different radii.
Warner and Drummond, yep. Just so you get an idea about how many eggs he eats. There we go.
That's impressive.
All right, so to find our volume of the egg, we decided to have an experiment rather than just Googling. So step 1, we selected an egg, like from a carton of 12. Pretty
A dozen,
high-tech.
really.
Yes.
And so we wanted to be able to take the radii, and in order to do that, we decided to hard boil it so we could actually cut it open and measure.
Exactly, so we put it into a pan of water and we boiled it. Yeah,
Hardly.
yes. And then since this is a Disney presentation, we decided the egg had to be a princess. Her name's Egora, friends call her Egg. It's a Hercules reference.
It's funny.
Yep. And then, Brianna, what did you do next?
I peeled her skin off.
Yeah, it was a little violent that day.
I did that.
And then I cut her into 4ths.
Yeah.
Egg sacrifice, as singular. And then we took a ruler and we measured her insides.
Exactly.
Yeah, let's see what those measurements were.
Okay, like I said, the volume of an ellipsoid is 4/3 pi r1 by r2 by r3.
And as presented. So RR1 and RR2 and RR3 was roughly 2.8 centimeters, 2.2 centimeters, and 2.1 centimeters.
So we plug those little numbers into our equation, and we get a volume of 54.186 centimeters cubed.
So if we multiply that by our 60 for Gaston's 5 dozen eggs, we get about 3,251.171 centimeters cubed.
So if you picture this, it's like taking a carton of milk, of liters, and having about 3 1/4 of them, just like shooting them down for breakfast.
Except instead of milk, this is eggs.
It's a lot more appetizing.
Yeah, it's pretty great. So our next segment is Cinderella's carriage. Because you see, when we were watching this movie, we were looking and the fairy godmother took this pumpkin and all of a sudden it starts growing into a carriage and we're like, related rates, right there.
We didn't even think of the carriage being magically made. It was related rates.
Exactly. Exactly.
Okay, so Cinderella.
So the earliest recorded version of Cinderella was written in China by Tuan Shengxi in the mid-9th century.
So the Grimm brothers also wrote a version of the tale, Aschenputtel, or Ash Girl, in 1867. Charles Perrault also wrote one. He wrote a version that introduced the fairy godmother, which is the one who is turning the pumpkin into the carriage using related rates.
Pretty great. So Disney released its version in 1950. It's been a pretty big success, and it focuses on a deprived girl forced to slavery for her evil stepmother and stepsisters while she follows her dreams.
She wants to go to the ball to find love.
And she does. She has small feet.
Spoiler alert, Laurel, you just told them the whole story.
I'm sorry, why don't we talk about the history of related rates instead,
Well,
Brianna?
that sounds even better. Okay, so related rates are used to show the derivative as a rate of change and to demonstrate implicit differentiation.
And it originated around 1836, give or take a few months.
So William Ritchie is our professor of natural philosophy at London University, and he published principles of differential and integral calculus in order to show related rates.
And the purpose of related rates was to simplify the presentation of calculus so that those not in college could understand it.
So it's basically on the main principles of geometry and algebra all the way up to advanced quadratic equations. So those are the ones applied so those not in college could be able to do related rates.
Exactly.
And watch Cinderella.
And Ritchie drew upon Newton's concepts to develop a fundamental explanatory process that evaluates the change in magnitude over time. Yeah. For your enjoyment, is it about here?
Yeah.
Ready? Ta-da.
Related rates match.
Pretty great.
Pretty amazing. So this is our math.
Yes. So, because the carriage is so spherical, we decided to assume that the pumpkin is spherical also. And so for our volume formula, we used 4/3 pi r cubed.
To find we found the derivative of that to find the change in volume. So we got an equation of 4 pi r squared times dr dt.
And we're looking for the rate of change in the volume. We didn't say that before. So, to find our dr dt, we had to assume that the radius is growing at a constant rate. And so we took our 2 points. Oh wait, I should explain where we got these measurements. We looked up on the internet and found out that there is a Cinderella pumpkin, like
actually
a
based
literal
on the one.
pumpkin that was inspired the movie, you know. So we have measurements for that.
It was originally a French name.
Yeah, it's Rosy de Dampe, and it has a 12-inch radius. So, pretty big deal.
And then we also had to find the measurements of our carriage, so we also did some research, and we found an actual replica that someone actually made of the carriage. And so we just took that measurements because they had it nicely there for my taking to my related rates.
So the radius of the carriage is 34 inches. And then we timed out the time at which the fairy godmother is turning the pumpkin into a carriage in 5 seconds. So that gives us our points to find the average rate of the radius change. So, you know, secant line, slope, y2 minus y1, yada yada yada, found out what it is.
DRDT of 22/5 inches per second.
Exactly. Okay, so, nope, never does. So then we plugged in our points at that for the DRDT, and we were able to find that the rate of change of the volume is 7,962 thousandths inches cubed per second.
And the change in volume at our time 2, which is at 5 seconds, is 63,917.587 inches cubed per second.
Yep.
Match. With 3 exclamation points.
All right, so this great movie came out this year. we were a little obsessed.
And we're like, we have to do math with it, obviously.
Exactly. I saw it 3 times in theaters, and each time I was like, wow, math.
Calculus. Math.
Exactly. So, the history of Frozen. It was a top-grossing animated film in the box office history, and it made $1 billion in global sales.
It was released in on November 27, 2013, and is loosely based on Hans Christian Andersen's Snow.
Although Disney took a couple liberties with Hans Christian Andersen's version, in that the Snow Queen is originally a villain, but Elsa is not. Elsa's pretty awesome. Elsa's just misunderstood. So, and it also follows her sister Anna, who's going to rebuild her relationship with Elsa, and meets a pretty cool mountain man and a snowman and all that good
And
stuff.
they're singing.
Yeah,
That wasn't in the original story either.
Nope.
And it is now. So we're gonna find our history of calculating falling objects because within the movie, they fall off a cliff. Spoiler alert, but they fall off a cliff. So Aristotle came up with this theory that all objects had a natural state of rest on the earth, but contact caused the object to move toward the center of the earth. And Thomas Brodwardine elaborated on that, and in the 1500s, he also developed a theory involving the speed of falling bodies. I don't know how he did it with falling bodies, but he did. And he claimed that the speed was equal to the ratio of the motive power and resistance. Although we know that is partially incorrect because it implies that velocities are always reached instantaneously,
Which is not true.
which is not true.
Galileo also had a theory in the 1600s that the distance a body falls is proportional to the square of time. And then our favorite guy, Newton,
Has the law of gravity.
yeah,
Yeah.
he's our man,
He is our man.
aside from Walt Disney. All right.
It's a 100-foot drop. It's 200.
Okay, so we don't actually have a clip of them falling because it's a new movie and you don't actually have the rights for that. But as you heard, Christoph said it was a 200-foot drop. Now, is it really a 200-foot drop?
Is it really? How is Christoph's math? That's what we're finding out. So, using our position formula, 1/2 AT squared plus V initial t plus height, we developed our equation.
So Christoph said our height was 200 feet, and we're gonna change that and convert it into meters. So we have our conversion of 0.3048. So we have 60.96 meters, and because gravity is our acceleration is negative 9.8 meters per second.
And all right, so at time 0, we set up our equation so that it's negative 4.9 t squared plus 60.96 because they don't have an initial velocity when they're falling. And by solving that equation, we find out that if they were really starting at that height, it would have taken them 3.527 seconds to reach the bottom.
But in the movie, they reached it in 2 seconds. So either the gravity is different in Norway, or Christoph is wrong.
He's probably wrong, actually.
It's probably wrong.
Yeah.
So, if the real height after 2 seconds would be about 19.6 meters tall, which is between 60 and 70 feet. So honestly, Anna was actually closer, which just proves that women are smarter than men.
Alrighty, so why does this matter? I put out a pretty good analysis of this. It's a proof. So Disney equals dreams, dreams equals hard work equals calculus. Therefore, due to the transitive property, Disney equals calculus.
So yeah, and they all lived happily ever after.
Questions?